Okay, hello everyone. Let's wait for a few minutes. More people may join. Then we will start. Okay, hello. Can you see my screen? Can anybody tell? Please write in the chat box if you are not able to see the screen.
Yes, sir. Yes, sir.
Okay, fine. Okay, so the first question is
Sir, visible, sir.
okay, fine.
Sir, good evening, sir.
Yeah, good evening. So let's start today's session. Okay, so the first question is written a silicon. বন্ধ করো তো নেটটা। Okay, sorry for the disruption. I hope now you can see my screen. Okay, so the first question is a silicon semiconductor sample is kept at 300 Kelvin, which is doped with phosphorus atoms at concentration of 10 to the power 15 per centimeter cube. Now we need to find what is the position of Fermi level with respect to the intrinsic Fermi level. So, so this will be reference Fermi level. I mean, we need to find EF minus EFI. I means intrinsic. Okay. So let's try to find. So what will be the formula? So what we know is that so for donut type atoms, we have n equal to n, or let's say capital N donor, e to the power minus E minus EF by cavity. This is the general formula. Okay, so let me solve it. So from this, if we take log base E of n by nd, n is the electronic carrier concentration and nd is the donor atom concentration. So that will be minus EF by kVt. And we actually need to find EF minus EF intrinsic, right? So this is sort of intrinsic. When we call EF, we actually mean it is in EF for intrinsic case. So EF minus EFI. This part is the EF minus EFI. This will be kBT ln nd by n. Because of this extra negative sign here, this will be reversed. This we need to find. So kBT at room temperature will be 1.38 into 10 to the power minus 23 into 300 Kelvin, and if we take in EV, then 1.6 into 10 to the power minus 19, right? And ND is given as 10 to the power 15 per centimeter cube, and N, the intrinsic carrier concentration, is also mentioned, but here in the question, probably yes, I have not mentioned, but it is actually 1.5 into 10 to the power 10 per semi cube for silicon. So if we put all these information, then EF minus EFI intrinsic the answer will come out to be in EV. It will be 0.287 EV. Okay. This also makes sense because for N-type semiconductor, what really happens, this is suppose conduction band, this is valence band, this energy level, conduction band bottom is EC, and let's say we are starting from 0 energy, okay, 0 Kelvin, sorry, here it is 0 Kelvin, but along this temperature is increasing. Now initially at T equal to 0, let's say this is the donor energy level, so E donor. So what really happens, initially Fermi energy lies somewhere here above the donor energy. As the temperature increases, this actually becomes like this. So this goes below the donor energy level, and this is intrinsic Fermi energy. Okay, this is at 0 Kelvin, 0 K, and somewhere around this is, let's say, 300 Kelvin. The intrinsic Fermi energy EFI, and now we found that EF is somewhat lower, right? This much is lower, that's why it is comes out to be positive. But at 0 temperature, it actually above the donor energy level. Okay, so next question.
Sir, once again tell the answer, sir.
Okay, so the answer is 0.287 electron volt. So okay, so I can wait for few seconds. Okay, so next problem. So the next question is a hypothetical semiconductor has an intrinsic carrier concentration of 10 to the power 10 per centimeter cube at 300 Kelvin. Now it has conduction and valence band effective densities of states at so both Nc and Nv basically are equal to 10 to the power 19 per centimeter cube. Now first question is what is the band gap of that intrinsic semiconductor, and then we dope the semiconductor with donor concentration of 10 to the power 16 per centimeter cube. So what are the equilibrium electron and hole concentration at 300 Kelvin? So try to find this out. So anyone found the first answer, band gap? Okay, so let me solve it. So first we need to find the band gap. We are given intrinsic concentration to be 10 to the power 10 per centimeter cube, whereas Nc equal to Nv. So these are 10 to the power 9 per semi cube, right? And temperature is 300 Kelvin. So the formula for intrinsic, this is intrinsic, is intrinsic concentration is NcNv, sorry, V, and then e to the power minus kBt. Here Eg is the band gap. So this is somewhat uh, so somewhere there is valence band, somewhere conduction band, and conduction band concentration, carrier concentration is NC, there, sorry, NV, sorry, this is NC, conduction band, and for valence band this is NV, and we need to find this band gap. So just need to put the values. So this will be 10 to the power 19 into minus Eg by Kb into 300, and N is 10 to the power 10, right? So if we take log base E, 10 to the power 10 by 10 to the power 19 equal to minus Eg by so gap will come out to be 10 to the power minus 9, sorry, ev, and this will come out to 1.087 electron volt. This is the band gap. And the second part is we dope the system with Nd of 10 to the power 16 donor per centimeter cube. Now we need to find the equilibrium electron and hole concentration. So what law of mass action says, N0 P0 equal to Ni Pi, right? Now N0 is the new Nd donor concentration, which is 10 to the power 16 per centimeter cube, and we already know Ni, and for intrinsic case this Ni equal to also Pi. So this is, that's why we call it Ni square. So we need to find what are the equilibrium electron and hole concentration. So P0 Ni square by N0. Ni was 10 to the power 10. So Ni square is 10 to the power 20, and then by 10 to the power 16. It will be 10 to the power 4 per semi cube. Okay, so next question. So given that the density of states, effective density of states related effective masses of electrons and holes in silicon are approximately 1.08 and 0.56 times the mass of electron me, and it is also given that electron and hole mobility at room temperature are 1350 and 450 centimeter square volt inverse second inverse. Now we need to calculate the intrinsic concentration and the intrinsic resistivity. So intrinsic resistivity we can get from the by inversing the conductivity, and intrinsic concentration also we can find very easily with the formula. So try to find out and then I'll solve. Okay, so another information is given, although it is usually known, that band gap energy of silicon Eg of silicon is around 1 volt, not exactly but 1 electron volt. So if anyone have not solved it, let me solve it. So firstly we need to find the intrinsic concentration. So intrinsic concentration formula is a root of Nc Nv into e to the power of minus energy gap by kBt. Now we don't know Nc and both Nv, and for this Nc concentration at conduction band or effective density of states rather, this is given by the formula 2 into 2 pi effective mass of electrons kBt by h to the power 3 by 2. Similarly, effective density of states in the valence band is just we need to replace the effective mass of electrons with effective mass of holes. So we can easily find because we are given that effective masses, right? So if we put all these values, 2 pi into 1.08 into electronic mass means 9.1 into 10 to the power minus 31, 1.38 minus 23 into temperature is room temperature probably, or nothing mentioned means we will assume 300 Kelvin. And H. So this NC will comes out to be 2.8 into 10 to the power 9 per semi-cube. This will come in SI, but if we convert in semi-cube, then 2.8 into 10 to the power 19. Similarly, we can find NV, effective density of states at valence band, 1.05 into 10 to the power 19. Okay, so now also given energy gap is around 1.0 electron volt. So if we put all these information, then .8 initial minus 1.0 into 1.6 10 to the power minus 19 by kBt. So this will come out to be 10 to the power 10 per centimeter cube. This is the intrinsic concentration. Next, we need to find resistivity, which is inverse of conductivity, and we know conductivity in terms of mobility is given by n concentration of electrons, then electronic mobility plus np concentration of holes into mobility of holes. Now for an intrinsic material, number of electrons equal to number of holes. That makes the concentration of holes and electrons to be equal. So this modifies to mu e plus mu p. Intrinsic we just found out 10 to the power 10, and then the mobility. So 1350 and 450. This will be unit of ohm inverse, semi inverse. Okay, let it be. So then finally we need to find out resistivity equal to 1 by sigma. So if we reverse this, then the final answer comes out to be 3.5 into 10 to the power 5 ohm into centimeter. So this is the final intrinsic resistivity. Okay, so next question. So estimate the mean speed of electrons in the conduction band. So when it's a mean speed, then it is essentially in the intrinsic situation, meaning we have not applied any external electric field or any other type of perturbations. And there are given information like effective mass, we just take to be electronic mass. Then T is also 300 Kelvin. So only this much information. With this much information, we need to find, we need to estimate. This is just an estimation because this will not be accurate. Uh, for obvious reason, this effective mass never becomes exactly equal to the electronic mass. So any idea how do I find or estimate the mean speed of electrons? Okay, so for estimation, so we actually need what, mass into velocity square. This is the kinetic energy, right? And we just need an estimation. So why the electrons will move around? Because of its thermal energy. When there is no external perturbation, electric field or temperature gradient, etc. So the thermal energy for a three-dimensional electron gas looks becomes 3 by 2 kVt, and this actually comes from equipartition theorem of Boltzmann gas. So what do you mean by Boltzmann gas? Those gas or those particles which follow the Boltzmann Maxwell-Boltzmann statistics, and this actually generic version of this is to be F by 2 kVt, where F is the degree of freedom. So for a three-dimensional 3D electron gas, there are 3 degrees of freedom. If we don't consider spin, other part, of course, free for free particles, spin is not to be yeah, will define degree of freedom. But X, Y, Z. So there are 3 degree of freedom which contributes to 3 by 2 kVt. So this much is the thermal energy for 3D electron gas, free electron gas rather. So the thermal energy actually gives rise to the kinetic energy to the electrons. So we'll equal this and we need to find V. So 3 kBT by m root 3 into 1.38 into 10 to the power minus 23 into 300 Kelvin by, this is actually electronic mass we are approximating. So this comes out to be 2.3 into 10 to the power 5 meter per second. This is just an estimation. Okay, next problem. So the donor concentration in a sample of n-type silicon is increased by a factor of 100, and we need to find the shift due to this 100-fold increase of the donor concentration, shift in the position of the Fermi level at 300 Kelvin, given that the kVt is 25 millielectron volt at 300 K. So find out, and yeah. So what we really need to do in this case is the we need to find initial Fermi energy and then the final Fermi energy. We just need to take the difference, and that's why we do not need explicit information of let's say donor concentration and then NC, effective dose or effective concentration at conduction band, etc. Because that will come out to be ratio. So anyone found the answer? Okay. So what we really know is the concentration formula, right? N equal to, or rather, let me see once the formula. So this one, N equal to N D e to the power minus of E minus EF, the EC minus EF by KBT. This is plus or minus? Okay, plus. So if we consider that uh, initial case, then N equal to ND e to the power minus EC minus EF initial by KBT, and then final case will be N equal to ND 100 times the donor concentration has been increased, and minus EC minus EF final by KBT. Now we need to find the shift in the position of Fermi energy. So shift is EF, EF final, EF final minus EF initial. This is the shift in EF. So if you just divide equation 1 and 2, there will be 1 by 100 times e to the power minus so which will comes out to e to the power minus EFI minus EF final by KBT. So if we take log of that, this is fine. Okay. Log of 100 equal to EFI minus EF final by KBT. This EF initial minus EF final will be 25 MeV into 10 to the power 10 square, let's say. Okay, so this is in uh, log base E, so there is no advantage by writing ln 100 to ln 10 to the power 2, and the final answer comes out to be EF I minus EF equal to 115 MeV. So this is the answer. We can also express EF final minus EF initial. That's the minus sign will be there. Okay, so next question. So for an intrinsic silicon at 300 Kelvin, it is given that Ni value. Ni value means intrinsic carrier concentration is 1.5 into 10 to the power 10 per centimeter cube. Now we add the donor, and it is given that one impurity atom is added per 10 to the power 8 silicon atom. Then we need to find the conductivity after doping, given that electronic mobility is 1300 and hole mobility is 500 semi-cube per volt into second. So the formula for conductivity is again carrier concentration, then electronic charge, carrier concentration, and the mobility. So if any of you found the answer, then please write it in the chat box. Okay, so let me solve it. So this is the conductivity relation. When we actually add donor or impurity in general, then the conductivity increases mainly due to the donor concentration. Okay, so intrinsically we have some, let's say, electronic concentration, and then there is hole concentration which are equal. But we add donor just because we want to have that semiconductor, mainly because of donor. The conductivity increases mainly because of donor, and in that case sigma is given as NND, donor concentration, and mobility. Now this mobility will depend on the type of donor. So if it is uh, so type of impurity rather, so impurity can be two types: donor and acceptor. Donor gives rise to electron, gives extra electron in the system, and acceptor gives extra hole in the system. So whenever there is donor in the system, then the mobility will be electronic, right? Electronic mobility, because the primary conducting carrier becomes electron in case of donors. So this will be used. Now we need to find ND, and ND is given as 1 impurity atom per 10 to the power 8 silicon atom, right? Now how many silicon atoms are there, or the concentration of silicon atom is this 1.5 into 10 to the power 10 per centimeter cube. This will be the concentration of donor. Just a second. This is actually wrongly quoted here. This will be 5 into 10 to the power 22. Okay, so two things here. In the question, this is mixed up. 1.5 into 10 to the power 10 per semi cube. So this is actually the intrinsic concentration. That is okay. That is correct. Now another information is there, which is there are 5 into 10 to the power 22 atoms of atoms per semi cube. So this is silicon concentration. Okay, NCI we can say, and this is charge carrier concentration. So need to multiply by the silicon concentration, because the concentration is given as 1 impurity atom per 10 to the power 8 silicon atom, right? So the concentration of silicon is 5 into 10 to the power 22 atom per centimeter cube. So the concentration of donor will be 5 into 10 to the power 14 per semi cube. So then sigma we can find electronic charge, and then Nd, sorry, 14, and then the mobility of electron, which is 1300. Finally, the answer will be Ohm inverse, semi inverse. So this is the answer. Okay. So next question. So next we go to few problems on magnetic properties. Ferromagnetic material has a Curie temperature of 100 K. Then the options are first option is its susceptibility is doubled when it is cooled from 300 to 200 Kelvin. So all the atomic magnets in it gets oriented in the same direction above. And then third option, third option is the plot. Sorry, the plot of inverse susceptibility versus temperature is linear with a slope of Tc. Tc is the transition temperature. And last option, So the plot of its susceptibility versus temperature is linear, but this is now with an intercept Tc. Initial, sorry, the first or the sorry, not first. The option third C was the slope Tc, and the last one is intercept Tc. So yeah, try to find out. It will be easy. So ferromagnetic material has a Curie temperature of 100 K. Tc is given. That means this is Tc. Anyone found which options is correct? Okay, so let's see the first option. What is the susceptibility of a ferromagnet? Susceptibility chi. This is susceptibility. Chi is given as some constant T minus Tc. T is the absolute temperature and Tc is the transition temperature or Curie temperature. So if we see the first option, let's try to find out at T equal to 200 Kelvin, what is the susceptibility? Susceptibility becomes C by 200 minus 100 because Tc is given as 100 Kelvin. So this becomes at T equal to 300 Kelvin, C by 300 minus 100 equal to C by 200. So you can actually clearly see that let's call it 300 and it 200. So you can clearly see that 300 Kelvin 2 times 300 Kelvin susceptibility is the susceptibility at 200 Kelvin. So option A is the correct answer. So although we got the correct answer, but let's look at the other options. All the atomic magnets in it gets oriented in the same direction above. Not necessarily. This is not necessarily true. Of course, majority of the atomic magnets or the magnetic domains are oriented in some direction so that there is overally some magnetic moment in the system, but all of them are not necessarily in the same direction. So in the ferromagnetic material there happens to be some domains. These, let's say this is this in this domain there are they are directed along this direction, then in the next domain there may be directed along slightly different direction. This will be all parallel. Then in the next domain there again some slightly different, and all these overall magnetic moment not equal to 0 for a ferromagnetic material, but not necessarily all over the sample the magnetic moments are all aligned exactly along the same direction. So second option doesn't meet the criteria. Then third option, the plot of inverse susceptibility versus temperature. So let's first do that. So let's first plot chi, then we will plot inverse susceptibility. So chi equal to C by T minus Tc, right? So let's say this is Tc, then it look like for temperature for T greater than Tc, this is given as hyperbolic type function, right? Then if we plot the inverse from that, this will be, so if we plot 1 by cow now, 1 by cow, so chi inverse equal to C inverse into T minus Tc. Okay, so this is become congested. So let me move to the next page. So this is actually linearly. Chi inverse is linearly proportional to T, above, of course, above Tc, when T is greater than Tc. So this is the case. So what we really see is that uh, so let's look at this equation and this equation and look and try to read the option C and D. The plot of inverse susceptibility versus temperature is linear. That is okay. That's what we found, linear. And then it is with a slope of Tc. But that is not the case, right? From this we can see that this is y equal to mx type equation where m is C inverse. So slope is not Tc. Slope not equal to Tc. Rather it is equal to C inverse. So third option definitely doesn't work. Then it says plot of its susceptibility versus temperature is linear with an intercept Tc. Now the plot of susceptibility versus temperature is not linear at all. So the fourth option doesn't also hold. So these are just to show you that what the plots of chi and chi inverse looks like. We already found the A to be the correct answer, but anyway. So next question. Okay, so the energy of a ferromagnet as a function of magnetization m is given by function of m. F of m is f0 plus 2 times t minus tc m square plus m to the power 4, where f0 is greater than 0. We need to find the number of minima in the function f of m for t greater than tc. So options are 0, 1, 2, sorry 3 or 2. So this f of m is actually comes from the Landau theory, Landau phenomenological theory of magnetism, f of m. Phenomeno theory of magnetism. That's a different story, but now we need to find the number of minima for t greater than tc. This is just pure mathematics. So anyone found how many minimas are there? Okay, so let me solve it. So the function of m is given as f0 plus 2 tc m square plus m to the power 4. So for minima, how do we found? Del f m, del m equal to 0, right? So this will be 0 plus 2 into 2m plus 4m cube equal to 0. So if we take common, then 4m, so t minus tc plus m square equal to 0. So there are two conditions. First condition is either m can be 0, that is trivial solution, trivial solution, and then second condition is m square plus t minus tc is 0. Actually, you can question that how can m square be equal to minus of t minus tc from this expression, right? Actually, there remains to be some in f of m. There is f0 plus some constant a by 2 or 2a, whatever. Then m square into t minus tc. This is the actual formula, but we ignore that constant factors a, b, and the dimension actually factored into in m and t. Okay, so there is nothing wrong in writing this way. So m equal to plus minus root of t minus tc. So this is another solution. Second, now we need to find minima. This was the extrema, right? So if we strictly say this is the condition for extrema, that can be minima as well as maxima. So for minima, we need to find double derivative. So double derivative will be 0 plus from this expression plus 4 into t minus tc and then 12 m squared. Now let's find both the condition on when equal m equal to 0, then del 2 f del m2 becomes 4t minus tc. Second condition, m equal to plus minus root over t minus tc, del 2f del m2 equal to 4t minus tc plus 12 into t minus tc, right, m square. So this, let's put it this way, plus minus into square, or this is root over. Now we will analyze both the cases. First case, let's analyze the first case first. For m equal to 0, this del 2f del m2, this will be greater than 0 when t greater than tc, right? And we need to find for t greater than tc. Now there are other options as well. This when t greater than tc, the second option gives us 4t minus tc Let's write that clearly. So this will be m square equal to minus of t minus tc. Okay. Then it will be m equal to plus minus Tc minus T actually, okay, not the other way around. So here it will be Tc minus T. So plus 12 Tc minus T. Then it will be minus of 8T plus of 8Tc. So 8 minus, this will be less than 0 when T, sorry, T is greater than Tc. So there are two conditions, two different condition of positivity and negativity. So for T greater than Tc, for m equal to 0, this becomes positive. Now for T greater than Tc, the second option of m gives rise to negative a. Here it will also change. And for minima, we know the second derivative becomes positive. Minima of a function, the second derivative of that function is positive. So m equal to 0 is the correct case for us, and so m equal to 0 is the only minima for T greater than Tc. This implies that there is only one minima for T greater than Tc. So the correct answer is B, 1. Okay, and it is also consistent because Landau theory of magnetism, rather phenomenological theory, it is the f of m versus m. It actually looks somewhat like this. This is for T greater than Tc, and T less than Tc, it becomes, so this will be symmetric, but anyway, sorry. So these are the two minima. This is minus m and this is plus m. Here minus m and plus m. And this is for T less than Tc. And physically, how can I understand? Physically, we understand this because when the sample is greater than Curie temperature, then there should not be any magnetism, right? That means, or magnetization. That means m equal to 0 is the ground state. F of m is actually F of m is actually called Landau free energy. So free energy becomes a minimum in the ground state. So for T greater than Tc, the m equal to 0 is the ground state. So T greater than Tc, m equal to 0 is ground state. Okay. And for T less than Tc, m equal to plus minus m, or rather we can also call m0. Okay, m0 is ground state because free energy becomes minimum here, and So at plus m as well, at minus m, and this energy is same. At plus m the energy, and minus m the energy is actually same, and there is spontaneous transition between plus m to minus m, which is called Goldstone mode. That's a higher order theories, but these are the physics. Ki when you go below the Curie temperature, that is transition temperature, you get finite magnetization. This implies once we are above the Curie temperature, then there is no magnetization, meaning m equal to 0. Okay, so next question, ninth. Okay, so let me explain, draw the figure, then explain. O is the origin, and this cutoff is given as minus 2 into 10 to the power 4 CGS unit, and this transition temperature is 600 Kelvin. So the question is inverse susceptibility as a function of temperature for a material undergoing paramagnetic to ferromagnetic transition is given in the figure. Now the value of Curie constant and molecular field constant we need to find with the data given in the figure. So let's solve this. Magnetic susceptibility is actually given by C by T minus gamma into C. This actually represents Tc. Now we need to, first of all, we need to find C equal to what value, and then also molecular field constant. And this molecular field constant is gamma inverse. Okay, so we need to both find gamma and C. So let's see how we can find this. So this is at t equal to 0, right? Now let's say chi at t equal to 0 becomes C by 0 minus gamma C, means 1 by gamma minus. So this is chi inverse equal to minus chi inverse equal to gamma. So then gamma becomes minus chi inverse at t equal to 0. And from this figure, chi inverse at t equal to 0 is given by 2 into minus 2 into 10 to the power 4 CGS unit. So gamma becomes 2 into 10 to the power 4. Okay, so this is gamma. So their options are wrong. This doesn't seem to match any of these actually. So anyway, the correct is we need to find gamma inverse. So gamma inverse options are actually given wrong, because 1 by gamma should be 1 by 2 into 10 to the power minus 4, which will be 0.5 into 10 to the power minus 4. Is there any option of, okay, there may be correct option, 5 into 10 to the power minus 5. Yes, there is lambda equal to gamma inverse. So this is 5 into 10 to the power minus 5. So we already got the correct answer B, because one option is correct and nothing is matching. But let's also try to find the C. How do we find? So to find C, we have chi inverse, second part, chi inverse equal to 0 at t equal to, sorry, 600 Kelvin, right? At, at this point chi is 0, 600 Kelvin. So then chi inverse equal to uh, 0 means this will imply that C by T minus gamma C inverse equal to 0. That means T equal to 600 Kelvin minus gamma we already found. It will be 2 into 10 to the power 4. 2 into 10 to the power 4 into C by C equal to 0. This implies that C will be 600 by 2 into 10 to the power 4, which is 3 into 10 to the power minus 2 CGS unit. So this is the correct answer. 3 into 10 to the power minus 2. This is also there. Okay, so this was the solution. We just use two values. Chi inverse at t equal to 0 is given, minus 2 into 10 to the power 4, and chi inverse at t equal to 600 is 0. So these are the two conditions, and then we just need to find this from equation. Okay, so let's end the session here. Thank you for joining. In the next session, we'll do further problems on magnetism, and maybe which week 11 covers basically. Okay, so I'm ending the meeting.